What causes chaotic behavior in unstable amplifier circuits? Imagine a simple amplifier suddenly behaving like a wild storm, with signals jumping unpredictably. That's what chaos looks like in electronic circuits. When circuits become unstable, they can produce irregular, unpredictable signals instead of smooth, steady ones. So, what makes this happen? It all comes down to how the circuit's feedback and components interact. In an amplifier, active parts like transistors or operational amplifiers boost the input signal. For the circuit to work well, it needs to stay stable, meaning the output settles down when the input stays steady. But if the feedback loop, which controls how the output influences the input, is not designed properly, things can go wrong. When the feedback introduces phase shifts or gain conditions that push the system past its stability point, oscillations start. Instead of a clean, predictable output, the signals become irregular and chaotic. One big cause is nonlinear feedback elements. Unlike linear components that respond proportionally, nonlinear parts can behave unpredictably. For example, if a resistor or transistor hits its saturation point, it no longer responds linearly. This causes the circuit to follow complex equations that can lead to chaotic solutions. It's like pushing a swing too hard and causing it to wobble wildly instead of swinging smoothly. Another factor is the presence of multiple reactive components like capacitors and inductors. These create what are called poles in the system's transfer function. When combined with nonlinearities, these poles can produce complex oscillations. Instead of simple sine waves, the output can become a jumble of unpredictable signals. Positive feedback also plays a role. If the feedback loop unintentionally reinforces the output instead of stabilizing it, the circuit can become unstable. When the phase margin, which is the buffer before oscillations happen, is too small, the system can suddenly start ringing or oscillating chaotically. Parasitic elements like stray capacitances and inductances in real components can also cause chaos. These tiny, unintended effects alter the frequency response, reducing stability margins. When these parasitic effects are significant, they can push the circuit into chaotic behavior. Lastly, these chaotic behaviors are highly sensitive to initial conditions. Small changes in input signals or component values can lead to big differences in output over time. That's why a tiny variation in a resistor or input voltage can turn a stable amplifier into a chaotic one. From a signal processing perspective, these behaviors come from the nonlinear differential equations that describe the circuit's feedback and component interactions. For example, circuits like Chua's circuit are famous for showing chaos because of their nonlinear resistor and feedback structure. They are modeled by coupled nonlinear equations that produce unpredictable signals. In real-world analog signal amplification, chaos is usually undesirable. It distorts signals and makes control difficult. Engineers combat this by adding resistors to dampen oscillations, using snubber circuits to suppress high-frequency ringing, and designing feedback networks with enough phase margin. Proper PCB layout also helps minimize parasitic effects. In summary, chaotic behavior in unstable amplifier circuits is caused by nonlinear feedback combined with reactive components that create complex, unpredictable interactions. Understanding these factors helps engineers design more stable, reliable circuits for signal processing and control systems.